Hello everyone, I'm Alexandre Mazel. I work at Aldebaran in France on a lot of subjects related to applied research, exploration and innovation. In this webinar, we're going to talk about creating your own vision algorithm directly in Python. First, I will quickly introduce the company and the NAO robot. After that, I'll explain you how to develop vision algorithm in Python and why. Then I'll show you how to integrate this algorithm in a complete choregraph behavior. And finally, we'll talk about performance and how to port your algorithm in C++. But why? It seems so silly. But let's quickly talk about the company and the robot. Aldebaran is a French company. We are more than 400 employees and we have sold more than 5,000 NAOs all over the world. We are the worldwide leader in humanoid robotics at school. We provide lots of contents for the teachers to use in the classroom. You can see here 3 examples of books full of exercises to learn about the technology, about how to program the robot. These books are available for you to create your own classes based on full exercises. As you already probably know, NAO is a fully programmable humanoid robot with a lot of sensors and actuators designed for interacting with humans. So, it will be able to recognize humans, speak in various languages, walk, connect to any network using Wi-Fi, and it is fully programmable. If you're interested in everything it can do, you can connect to our YouTube channels. There, you'll find plenty of video featuring NAO in various situations. With the robot comes some softwares like CHOREGRAPHE, that is a graphical development environment, enabling you to develop complete behavior, including nice movement animation. We are also providing WebBots, a physical simulation engine, so that you'll be able to simulate all the physics and interaction with environment to test programs. Monitor is a small software to visualize anything coming from the sensors of the robot and also visualize the image seen by NAO. We're also providing complete SDK to program NAO using C++ or Python, like we will speak about today. But let's talk about image processing in Python. Here is the NACO vision architecture. When the user wants to get images from the camera, he subscribes to the NACO module, the video device. Then the video device will communicate with the camera driver to get new images. These new images will then be received by the user code. It's important to understand that the user code can be executed directly on NAO or on a remote computer. Usually, the user code is in C++. C++ is great because the generated code will run fast on the robot. So, you decide to write your program in C++. But before testing it, you must first compile the module using the same library that are present on your robot. We call this process the cross compilation. It's a bit tedious at first, and you'll need a computer running Linux. Then you send the binary to your NAO. You have to restart NAOKey. Then you test the new code and see the results. And you have to do that after every modifications. So it will take you a long time even to develop a simple vision extractor. On the contrary, developing your code in Python in some IDEA or directly in CHOREGRAPHE is very simple. You just type your code, then run it using F5. But yes, accessing the image pixel per pixel to process it in Python will be very slower than in C++, unless we found another way. But first, let's see how we can get the image in Python, then we will discuss about the process. To get images in your program, you need first to subscribe to the video device. You'll have to specify the camera you want to use, which resolution, an approximate frame rate, and the color space. At the end of the program, don't forget to disconnect from the video device so the video device will stop acquiring images. You can see that every client is recognized by a name. It's a string. After that, every time you want an image, you ask the video device for a buffer. The buffer is a string, so we convert this buffer in a more versatile type, a numpy array. Don't be afraid by that complicated line, the one with the from buffer method, and all the strange parameters. It's the worst we'll have to see today. So, this is our new method to return an image buffer to Python. Now, each time we call this method, we get a numpy array, and it's when it becomes a bit magic. We will never access to the pixel one per one. Instead of that, we'll use high-level method from external library like numpy or opencv. So, instead of iterating over a loop to have the average luminosity, you just call the average method, avg, on your buffer. Instead of developing your own convolution filter or feature detection, you can directly use the one from opencv. So, you're in the Python world, in your armchair, developing, testing, and tuning fastly your algorithm directly from CHOREGRAPHE. And because all the high-level methods you'll use are in some external C++ method in those third-party library, they are running the same speed as if you're developing yourself in C++, cross-compiling and so on. And best of all, if one day you want to redevelop your final program directly in C++, all the opencv calls would be quite the same. We will see that at the end of the webinar. So now, let's work on a practical example to show you how simple it is to use numpy and opencv from Python. We want now to follow a white line. First, let's begin to develop a function that will detect the position and orientation of a white line. So, on the left, here is what's in now, from its position in previous slide. We, human, could easily find where is the white line, but let's see how we could teach now to detect it. First, we will apply an opencv convolution filter with a power meter to detect vertical contours. The result of the filter is on the right. Then, we'll binarize the image to remove all noises and small objects, like the chairs on the right. All the nearly black points are becoming full black, and nearly white are becoming full white. It's logical. Then, we will compute the abscissa of every left white pixel. They are here, in blue on the right image, but unfortunately, I'm not sure you can clearly see them. Then, we will calculate very roughly an approximation of the offset and orientation of the blue line. In our example, we use simple rough averaging, as we don't care about the precise figures. Here is the total code. You can see the different process we've just described. In fact, the hardest part was to find which method to call in numpy to have the information we need. For instance, argmax is returning the abscissa of the first white pixel, while numpy.where is returning the ordinate of this pixel. Okay, now let's see how to integrate this small vision extractor in CHOREGRAPHE. So first, let's jump to CHOREGRAPHE. Okay, here is CHOREGRAPHE. We create a new box. It's a flow diagram box, named line follower. A flow diagram is just a box that contains a lot of boxes. In this box, I will create another box that I will name something like line detect. It's a script Python box. And I'll write a small tooltip for feature generation. Okay, and so I edit the code. I edit the output. I create two outputs One is when there's no line detected, and the other is when there's detected line. Up, magic, it appears instantaneously. So I edit the script. I will add a parameter. It's the period of the refreshing. Again, a small tooltips. I like the tooltips. I like the commands too, but you already know it. Oh yes, and version number. So this will be a period. I set a minimum, a default value, and maximum just for the fun. Again, I will use my magic power to make the code appears instantaneously. So with the detect line, we just write in the previous slide. You can see the method to connect to the camera, the method to disconnect from the camera, the small method to get the image from the camera. The method names are very explicit. That's great. Then you can see the way to get the parameter from the box. So it's the parameter we set previously. So we'll call detect line. If there's something, we tweak the output detected output, or we tweak the output non-detected. Here you could see the parameter we have in the previous box. Then there's a stop method. In the stop method, we put a boolean to true. Then the loop is stopped, and don't forget to call the stop method from the unload method, or else it will never stop. That's sad. Okay. So here is the final contents of the line found our box. You could see we had a small box. This box is very important. It will set the pitch of the head. Well, let's see what does the head pitch parameters. First, we have to see what is seen by the robot. Here is currently what's in my robot, so it's the top camera, and we want it to be, and we want to use the bottom camera. So let's make a small behavior on the fly to switch to the bottom camera. So this is the bottom camera. Let's see the result. Tack. So here is the line seen by now, and I'm going to explain you why it's so important to set the right pitch. Let's see what is seen again. I click on the head, and so we will see the various possible position of the pitch. You see, if it's too low, you see the fit, and so you can detect the line. And if you see too high, you will see the garbage of my office. So it's not right. Hello. So you have to put average value. This one is good. You see the end. Now it's okay. Okay, and this parameter, you have to put it in the box, in the head pitch box. So here is a small box to convert the position of the line to x, y, and theta parameters of the walk. Then we will output value to a standard OmniWalk box, just a walk that refresh the OmniWalk parameter and send them to motion. Then at the end we have to stop. And so we set the white period of our detector. We put 400 milliseconds because the OmniWalk don't handle a faster refresh. Here it's a small timeout. It's a box to program a timeout. It's when nothing is detected. It will trigger a memorize box. The memorize box is just a box that stores a value and output it when the start input is triggered. So here we just want to memorize the last value, the last position of the line. So if the last position is quite centered, if it disappeared, it's for sure because it's finished. Or if it's not centered, it's because perhaps we're lost. So we had two funny sentences to differentiate these two cases, and we hope it will work. Sometimes it works, but I must admit it don't work every time, but it's just a funny sentences. And don't forget to set the right camera settings, so every time you start your behavior, it's connected to the right camera, that is the bottom one. And so we start so when the box is started, you see the small square on the left. It's triggered when we start the box. Now we launch it, and so it's okay, it's launched. We see what is the robot. Okay, it starts. The robot is working. We're just in my office. It's a small one, so the line is very short, and so my robot hasn't a lot of time to work. So we would move to my playground. But first we need to add a small box to make the behavior easier to shoot a video. So I add a small tactile head box. It's just a box that will trigger events when I press the front and rear of my tactile sensor. So when I press the front, it will start the box, and when I press the rear, it will stop the box. And so I move up, we're moving. Okay, and now let's launch the behavior, and I shoot it from the outside. Okay, and so you see is following the line. It's a longer one than the one at my desk, and so I add, in this one we made a circle to add more fun. So there it's a bit on the side, and so up here, seen it's finished. Okay, let's go back to the slides. Okay, now for the curious, we will speak about porting the previous code to C++, so we could compare the performance and discuss about things and stuffs. As a filter in Python, and then the magic code were written in C++. Okay, I'll let you the time to read it. Here's a thresholding pass method. Here's another example. In C++, we have to write loop by the end. We can see that Python and numpy help a lot when the task needs to navigate through array. So it's easier, but perhaps less readable, but it's you to decide. Okay, I think you've got the pictures. Let's see the performance measures. As the results, you could see we are 4 times slower in Python. Hopefully we haven't worked at pixel per pixel level, or so it will be 20 times slower or worse. For this kind of behavior, the loss of time isn't really a problem, as the omniwalk method can't be refreshed faster than 400 milliseconds, so it was the right choice to use Python. About developing time, developing the vision extractor in Python takes me less than 2 hours, but just to port the module to C++, it takes more than 4 hours. And because it was already fine-tuned, 2 compilations are enough to have it working correctly on my NAO. But if we have had to create it from scratch in C++, I think we will need roughly 2 days or more. So it was really the right choice to use Python. This presentation is now finished. I hope it pleased you and that you will now all be able to create your own vision program. If you have any questions, I will be happy to answer, so please use the chat box to ask them. We'll stay connected here a few more minutes, so please use this opportunity to ask everything you need to know. Thank you, and don't forget to have fun.